Today we're given a bunch of equations like db equals 5 or root equals pp plus sj, and the question is, what is the value of root? So for pp we also have to evaluate an equation, and for sj we also have to evaluate the equation, so that will turn out to be simple tree recursion. Okay, so first of all, of course, we want to pass the string into a data structure. The idea is to put the left-hand side of the equation as a key in a map, and the right-hand side is then either a number or a more complicated calculation. Okay, so how do we actually do this? So we have another good old reseq here that passes the left-hand side. I call that A, then the colon, and then either a number or B op C. And then we check, did we actually pass a number? Then we want to convert that from a string to a long. Otherwise, we put B op and C into a vector. And this is the value in a map, and the key is A, the thing on the left. And the for comprehension gives us a sequence of those maps that will look like this. So a sequence of singleton maps with only a single entry. And then here we put that into one. We combine all those singleton maps into one map. And then that looks like this. Okay, so we should be able to work with this. Then here we have an evaluate function, given a bunch of equations and some arbitrary root. For parts 1, that's the literal root. We want to evaluate it. So here we define a function that is able to evaluate recursively. Given any left-hand side of an equation, any string A, we first ask inside the map, what's the right-hand side of that? And then we ask, is the right-hand side a number? Then we're already done. That's the result, nothing else to do. Otherwise, we destructure into B op and C, and then the operator is mapped from string to an actual function, right? So because, for example, plus is a function in Clojure. Okay, then we have a function, and then we apply that function to the evaluation of B and the evaluation of C. This is where the recursion comes in. So this eval is this eval. Okay, so this is a nice recursive function, and we start the process by applying it to our root. And for part 1, that is the little root as you can see here. So we pass our equations, and then we evaluate those equations starting at root. And that gives us the correct result. Now for part 2, the definition changes. So for part 1, the root was an addition and human had the value 5. And for part 2, this plus changes to an equal sign. So we want this to be true. And the question is, what's the value of human to make this equation true? And we could simply brute force it, but that would take much too long. I tried it up to 1,000,000 and that already took minutes. Right, so what do we do instead? How can we find a new equation for human? We simply search for an existing equation where human is on the right side and then rearrange that equation. Put human on the left side, and then the minus turns into a plus here. Okay. Then we have a new equation for human that depends on pt, but pt still depends on human, so they are mutually dependent. That can't possibly work. So we need a new equation for pt as well. Find an equation where pt is on the right-hand side, put it on the left side. Then we need a new equation for lg, find it on the right side, put it on the left side. Need a new equation for cc, find it on the right side, put it on the left side, find a new definition for pp. And here pp is the final case where we have the equality. So we can simply look, if these guys shall be equal, what is the definition of sj? Let's simply look above. The definition of sj is here, dr times db. So we simply replaced it with dr times db. Right? So this is then the last equation that we have to replace. Great, and that's exactly what the solve for human function shall do. So first we replace the plus with an equal sign. That was this replacement here. And then, well, we looked for lots of equations that had some given string on the right-hand side. And of course, I want to do that efficiently. So here I built a data structure. Let's look at the end result. For example, this formula here, or this one with a human inside it. This formula on the right-hand side has a human inside it and a dvpt. So why don't we have a a lookup table where the interesting operands are the keys and the equations are the values. So for every equation appears twice, once for the first key or this guy here, and once for the second, this guy here. Okay, so how do we do that? First, we remove all the entries in the map that resolve to simple numbers. They are simply not interesting to us. And then we can destructure the remaining equations into A, B, op, and C. And then we say B is in the equation and C is in the equation. Right, so these are the keys, B and C, B and C. Right. And then we start a loop. The equations are the equations that we just calculated here with the replaced plus to equals sign. And we initially want to solve for the human. So we ask our nice containing structure, do you have an entry for human? And then we will get this equation here, which we then destructure into A, B, op, and C. And then we ask, do we solve for B? Yes, because here human is on the left side, right? Okay, and then we simply check which operation is it. Maybe the comment is easier to explain. So if it's originally A equals B plus C and we are solving for B, then we need to put B on the left and A goes on the right then, and the plus turns into a minus. For minus, that turns into a plus, times turns into divides, and divides turns into times. Right, and later when we find the equals case, then we can say the right-hand side of the equation B is the same as the right-hand side of the equation C. That would be the terminal step. Okay, and for example, later if we want to replace dvpt, then that will be on the right-hand side. Then we have to solve for C instead of B, and that's just a bunch of different rearrangements. What's interesting here, so instead of B going to the left, now C goes to the left, and everything turns to either minus or divides, and the A flips from flips between these two positions. That's just how it turns out mathematically. Okay, so this is the meat of the solution. That was the hardest part. Right, and then for part 2, we can simply pass the equations again. Then we solve for human, then we get a new bunch of equations that we just built, and then we can evaluate not starting at root, but starting at human. And that gives us the desired result.